Okay, so yay. We are now entering another chapter, and this chapter is kind of neat. I like this approach because what we're doing here is really sort of a lot of hand waving, and it's successful hand waving. So let me just see if I have this set. So chapter 5 is about dimensional analysis, where we look at what's happening and apply it and look at how to deal with scaling things. So when you deal with real-world fluid problems, they tend to be limited to simple geometries and boundary conditions. And you often do a lot of work with experiments and computational fluid dynamics in order to sort of deal with more complex flows. And it generates, I mean, CFD, if you have tried to use the high performance computing available at U of T, they are very clear that they want to get rid of all of your data within 2 weeks. So we generate a lot of data, and then we have to get rid of it. And so using these types of approaches often prove to be very challenging. And so dimensional analysis is a technique to reduce the number and complexity of variables in a physical problem, presenting data in a more general, compact, and economic form. So just starting out with a simple example, why aren't there any small animals in the Arctic or at the poles? Heat loss is proportional to surface area, and mass is proportional to volume. Therefore, heat loss per unit mass is proportional to area over volume. So if I deal with a mouse, I have one over L, and it goes as 1 over 0.05 meters, or 20 to the minus 1, or 20, inverse meters. For a polar bear, 1 over L scales as 1 over 2 meters, and it's 0.5 meters, inverse meters. And so scaling is 40 times faster for heat loss off a mouse versus a polar bear. So a ratio of 40 to 1, which is kind of amazing. It's kind of amazing to think about the fact that you can just look at sort of the size of something and say, hey, that's why I'm not going to find a lot of mice in, say, the North Pole. They can't survive very long. Those of you who remember Gulliver's Travel, this is another example where we're looking at Gulliver, who is defined as being 12 times larger than the Lilliputians. And how much do you have to feed him? And how does that ratio sort of correlate to the people who are doing the feeding? So simple. If you look at the ratios of lengths, you can sort of say, okay, this is going to be something that would scale volumetrically. And that's going to be the volume of Gulliver over the volume of a Lilliputian, which is Lg over Ll, which is scaling as 12 LL cubed, which is 1,728 times. So 1,728 times more food. And again, it's a very simple calculation. You can sort of look at yourself, compare yourself to a mouse, do the same sort of thing, and you can see what your demands are versus a mouse. And it's really important to do this type of scaling for drug delivery. So, for example, even with relatively small differences in human scale, we often have very detailed charts and determinations for individuals. I do a lot of wind tunnel testing down in the bottom Roseburg underneath that lecture hall on the second floor. And one of the biggest problems, and the reason why we do it, and we've done it since 1880-ish, is that we can't test full-scale prototypes. So if you want to put a Boeing 747 in a wind tunnel, good luck. I don't think there's one that actually can hold one. There is up at NRC one that can hold full-scale Formula and NASCAR vehicles, and they do full-scale testing there. But generally, we do small-scale modeling. And one of the big problems with small-scale modeling is determining what exactly you're matching and how to determine what you're matching. So more typically, the other thing too, and this is something that you're on reading week, you need things to read, right? Yes. This is an older text or older book. And I know you can find a copy in the engineering library if you're in there. But it's Milton Van Dyke, Album of Flow Visualization. And a lot of the stuff that we talk about in the course, he presents from different authors. And so this is a Kármán vortex shedding. That's a cylinder on the far left. And this is done in water. And this is done with fluorescein. So it's not a great picture. In color, it's green. It really looks cool. Other tunnels are designed for different things. So up in Oshawa at Ontario Tech, they have an icing wind tunnel that's able to do temperature testing and very large scale models in there. There's also the tropic wind tunnel that can go from 0 to 165 Fahrenheit. These were the supercomputing of experimental methods, and they still remain relevant. Good to do experiments to sort of validate what you're doing. We do a lot of experiments, for labs. You'll see various types of wind tunnel. This is a very simple tunnel with an open return. And so flow comes in on the left and goes through to the right. And even though it's not super clear, that test section in there, you'd put in some sort of airfoil or an object and look at what's happening within it. We often look at drag force. And drag force, we start to look at things, say, for example, body length, stream velocity, fluid density, and fluid viscosity. And so, you might sort of put a cube in a flow. You have flow approaching V. You have a length that's associated with L, and you know what it is there. So you can say that this force is a function of length, velocity, density, and viscosity. And what your challenge is that if you want to look at all of these variables, you have to vary each of them. And so if you have to vary each of them, we have, say, for example, 10 L's times 10 velocities times 10 rhos times 10 mu's. you're looking at 10 to the fourth, which is 10,000. So you're doing 10,000 experiments where you have to vary all of those terms. Now, at this point, you're kind of already familiar with where this is going to end up. I can start to look at a combination of these variables. And if I start to look at a combination of these variables, one of them sort of comes screaming out at me. I have, again, function of force, L, V, rho, U, mu. And it will reduce to drag force, V squared, L squared, is equal to G, another function, this is not gravity, and rho V L over mu. So the left-hand term is drag force, or coefficient of drag, and the right-hand term is Reynolds number. And you've probably seen Reynolds number a lot at this point. So CF is just going to be a function of Reynolds number, and so CF is force coefficient which is force over rho V squared L squared, and Reynolds number which is just rho V L over mu. And as you're going through the course, this becomes much more important. These terms become much more important in the next two chapters, 6 and 7, because that's how we're going to start to define things. We're going to be looking at Moody diagrams. We're going to be looking at drag forces, skin friction coefficient, and all of that depends on these terms. Go ahead. Yeah, I regretted writing G almost immediately as I put it down in the note. G is a function. So it is not gravity. It is just a function of Reynolds number, a function of Reynolds number.
Okay.
And
G is not multiplying, it's a function of whatever.
yeah, that's right. So these are two functions. I don't have, and this is one of the things to be very careful as you non-dimensionalize. You're not getting you're getting order of magnitude relationships. You're not getting relationships. These are not, I can't multiply this by 10 and get coefficient of force out of that. So it reduces significantly the number of experiments that I have to do. And if you also start looking at some of the literature out there, you'll see this is how people present it. So typically, if I'm going to go publish this in a journal, they do not want to see values of force of 100 newtons, 2,000 newtons. They want to know what the drag coefficient is and the Reynolds numbers. And that way, I can compare my work to other people in the world. It helps sort of suggest how to group variables. So one of the things that often comes out is that I'm setting up an experiment. A graduate student is setting up an experiment. We discuss it, and we sort of do a back-of-the-envelope calculation to determine what do we need. And it identifies unimportant variables early on. So this is actually, I mean, it's as close to magic as you can get in fluid mechanics. You get a lot of insight from something that is relatively kind of painless to actually do.
So just by, like, if you have a Reynolds number, and because it's a function of 4 different variables, and you just so happen to have different combinations of those 4 variables that yields the same Reynolds value?
That's
so
correct.
We're so treating those 2 scenarios as the same?
Yeah, so one of the examples I'll do in the next chapter is looking at Reynolds pipe experiment. And we're going to say, look, Reynolds number of about 2,000 to 3,000 in that range is associated with the transition from laminar flow to turbulent. It doesn't matter what the fluid is in there. It's always going to be the same thing. Now, the funny thing about Reynolds pipe experiment is that if I want to torture a PhD student, I will ask them to design an experiment that will get up to 50 to 100,000, which is very large, very high speed, and maintain laminar flow. And it's possible. But the problem is that if their friend walks in and slams the door, the entire experiment sort of fails. So it's kind of neat to look at what you can do based on this sort of information and based on these scalings. So power scaling, so we have CF as a function of Reynolds number. And really what you're trying to do is match the Reynolds number of the prototype to the Reynolds number of the model. And the same thing with the force coefficient. And so if you do that, it's really good. Everything kind of works really well in my head. And I can match it based on sort of saying, hey, for the prototype, I can scale the model results to the prototype results by scaling the fluid. I'll typically use the same fluid, so that ratio will be 1. This ratio for the velocity of the prototype might be much lower, or well, higher, much higher. So, for example, if you're working for Boeing, Airbus, Bombardier, you're going to be operating in field with very high prototype and very low model velocity. And the length of the prototype, the length of the model are also going to be significantly different, at least on the order of 10. So even if I match everything else up and say for some remarkable reason I did match up velocities, a 10-time change in the prototype to the model is a significant change in terms of forces. So it's a factor 100, just for 10. And that's a pretty normal scaling. I wanted to go over question 2 because this sort of came up and the text is wrong, and so it's worth sort of going through this one very quickly. So you got an integral of density, velocity, time, and a volume element. And so if you remember from the past chapter, we were looking in chapter 4, we looked at these cubes dx, dy, dz. And that's going to scale as ml to the minus third, the 3. This is going to scale as lt minus 2. And just ignore that for now. And this scales as L cubed. So all of that together is just all what you needed, and I'm still trying to figure out what the text actually did here. I think they messed up with the del U del T term. All right. So it becomes ml minus 3, lt minus 2, L cubed and I have all of these terms together. So I have each of the terms separately, but I can start to group terms. And if I group terms like this, I can break it down into mass, length, and time. So that's just mass to the 1. That's going to be L minus 3, L1, L3, and that equals L1, and time minus 2, mL over t squared, which equal, well, there you go, that's what it equals. Okay. So again, mL t squared, and the dimensions of force. And so this integral is a force. So it's mass times acceleration, which you were used to. And then if you sort of put it up, you calculate it out, I guess I can rewrite this a few times and repeat that. Okay, any questions on this one? Go ahead.
Well, would it be easier for dimensional analysis instead of using ml and t if you just use like kilograms, meters on seconds?
No, because you do not want to limit yourself to SI units. So this is not a problem where, for example, if I had to deal with English, and I said to you, look, we'll have slugs and pound masses and pound forces, and we'll do this in inches and things like that, I would get still the same result. I'd get slug inches over second squared. If I do it in SI, I can immediately tell you it's kilogram meters per second squared, or newtons per, newtons. So it's a force. You don't want to limit yourself to a unit system. You can check afterwards and say, does this make sense? And SI is much, much better for that. But if you're really bored, you can put all sorts of units in there. Oh, I see. All right, I'll get this right. I have a copepod, a tiny crustacean of approximately 1 millimeter in length or diameter. We want to find the drag force in fresh water, and we build a 100 times scale model and test it in glycerin. So we go from water at 20 degrees C to glycerin at 20 degrees C. We have the length of the prototype, which is 1 millimeter. The length of the model is 100 millimeters. So the scaling is a little bit different than what we might normally work with. Velocity of the prototype is unknown. Force of the prototype is unknown. But at 30 centimeters per second, 0.3 meters per second, we measure a force of 1.3 newtons. At 20 degrees C, 1,000 kilograms per cubic meter, 0.001 kilogram meter second, and 1,250-ish kilograms per cubic meter for air, or water, or glycerin, and the model viscosity is 1.5 kilos per meter second. And that is what you're trying to model. So you can see it's very small. And I spent a great deal of time on Google trying to find a nice image of one. So just so you know, that sort of effort should be appreciated. So if you do that, you have a similarity condition, and it's rho VL over mu of the model, which equals rho VL over mu of the prototype. And Reynolds of the model is 1263 kilos per cubic meter, 0.3 meters per second, 0.1 meters, all over 1.5 kilogram meter seconds, which equals 25.3. This is a very low Reynolds number. So typically when you're dealing with flows or reality, say a pipe flow, we're looking at something on 10 to 100 to 200,000. If you're looking at aerodynamic flows, you're looking at things on the order of 1 million. So this is tiny. So if we set the prototype to 25.3, we can solve through for everything. And here we put 998. I'm not going to put units on it. VP 0.001. Point. Just want to make sure I have the right. Yep, it is 0.001 kilogram meter second. And solve for a VP of that, which is 0.0253 meters per second. And you can see that you've got thousands sort of multiplying through, and everything sort of, VP is going to be essentially, at the end of this, 25.3 divided by 1,000. So that's why you're getting that number. So if we do the same thing, we can say that force rho v squared L squared of the model is force rho v squared L squared of the prototype, and CF of the model is equal to 1.3 newtons over 1263, 0.3 squared, 0.1 squared, which is 1.14. And so if we set CFP of the model to 1.114, we can say 1.14 equals force of the prototype over 998.0253 squared, 0.001 squared, and force of the prototype is equal to 7.3 times 10 to the minus 7 newtons. So this experiment kind of goes the opposite way I normally would go. I'd be looking at a very large scale object, very high speed. In this case, I'm looking at a very small scale object, and I can measure the force acting on it a lot easier. If I try to match 1.3 newtons, I can measure that. I can't really measure this reliably. There are too many things that are going to go wrong in my experiment that I could ever set it up. And that's one of the reasons why you scale up when looking at very small micro animals, fauna. Any questions on this one? So just sort of beating into that sort of same point, I can't measure 10 to the minus 7th newtons. I can measure 1.3. And so if I can, then I'm better off, and I will get a decent result out of this. You can do the same thing with equations. And so again, if you look at Navier-Stokes equations, often you'll see it non-dimensionalized, but almost everything you can non-dimensionalize. If an equation truly expresses a proper relationship from variables in a physical process, it must be dimensionally homogeneous. And you already know this. You know that you can't add meters to seconds. And so one of the reasons why it's really important to write units, and despite the fact that I didn't in the last example, is that it helps you convince yourself you have the right answer. If you have something that is consistent in terms of units, it's often very helpful in calculations. And it means that every additive term in the equation must have the same. And you can't add force does not equal velocity. And this is really one of the reasons why you can do such remarkable things with dimensional analysis. So lots of people have looked at it sort of generally when we look at sort of the important results. Euler, 1765, wrote about dimensional reasoning. Fourier outlined this idea of dimensional homogeneity. Rayleigh proposed a method of dimensions. And Buckingham is the one thing that you will pull out of this chapter and remember for the rest of your life is Buckingham pi theorem. Dimensional analysis reduces complex problems to manageable dimensionless relationships. It saves a lot of time and resources in experiments and also in modeling. So CFD depends on this. Provides the basis for similarity and scaling laws, allowing for more tests, or model tests to predict prototype performance. The entire process is built on the principle of dimensional homogeneity. I kind of like that. So going back a little bit, we already did this one, so I don't need to do that again. Again, just the idea. So again, when you write an equation, when you write a relationship, you're not writing writing a relationship that says CF is equal to 10 Reynolds number. You're just saying there is a proportionality between Reynolds number and coefficient of friction, or force. Okay. When dealing with I'm trying to decide what to say here. Actually, yeah, okay. So I don't expect you to remember all of these relationships. You should know length, area, volume, velocity, acceleration. Speed of sound you should know. Volumetric flow, mass flow, sure. Pressure stress starts to get a little bit weird. Strain rate, angle, you should know that one. Angular velocity, viscosity. Viscosity, kinematic viscosity. I know that came up in the last midterm. Please try and write the relationship between viscosity and kinematic viscosity in your cheat sheet. Force, no, I don't. Force, okay, yeah, all right. I'm just going through the first half, pretty much you should know. The second half, we'd probably give you something to work with so you could figure it out. So various symbols are shown in the second column. But the third and fourth column are two different ways of doing the non-dimensionalization. I would say right now that the easiest way to do everything is to use mass LT. And force is a derived quantity in that case. And you can see that force is somewhere on that graph or on that table somewhere. I know. Oh, there it is, force. So it's a little bit more complex in this, but honestly, it's easier for you to remember everything, especially if you're used to SI units. And the only difference between the two is that MLT theta, theta is angle, mass, length, time, and the other one is force, length, time, and angle. This kind of table you should have available to you.
Do we get our own cheat sheet for the upcoming term test, or are you going to provide it to us?
I think
Curiosity of writing stuff like this.
I'll figure out what the cheat sheet is. We'll probably give you one.
Okay. So you're going to give us one and we don't write one. Okay.
What did you do on the first
We
midterm?
got both.
Okay.
It didn't help, but we got both.
Okay, all right. I'll probably continue to let you have both. Yeah, I'll do the same thing. It just doesn't make any sense to change it. But I'll give it to you in advance. You did you have it in advance?
Yes.
Okay. Then, okay. Yeah, if everything works out well, you should get it the Monday you come back from reading week, because I am not allowed to do anything during reading week at all. Oh, the McGraw-Hill is not a due that week.
Oh, really? Okay.
Oh, yeah. I checked that from the very beginning. No. That one, the only one I got right in that sort of all the due dates was that one. So I was very pleased with myself. Sorry. So, oh. So, a good sort of practical example, and one that you have done since first year. Go ahead.
I just wanted to ask, like we have an assignment due during reading week for this class, so
No, you shouldn't.
it's due.
Sunday is not reading week. Just so otherwise it would be too late with everything. The following Sunday is reading week. If you really want to sort of push on that one, I'm happy to push all of the due dates up far, far ahead. But this is a very fast-paced course, and I recognize that. And I'm trying to keep up with material that we're going to be testing you on. So I think it's a kind of, and this is assignment 5, right? Or assignment 6? 5. 5 is not bad. You already got 100% on question 2. Because the textbook got it wrong. Okay. All right, so if you look at that equation, you already know it's going to go and just be lengths because it has to be. But if you calculate each of the terms, write them out, and this is, again, one of the benefits of putting units down in all your calculations. The first term, s, is a length, s naught is a length, v naught t is length over time times time, which is a length. 1/2 gt squared is length. 1/2 doesn't have units, so we don't worry about that. L over t squared, L. Okay, this is where people got in trouble. So there was actually, G.I. Taylor was in the UK, and he used publicly available information to look at a nuclear explosion. And so nuclear explosions were brand new. Everything was kind of restricted. However, while the information was classified, the photos were not. And so you have there a relatively primitive high-speed camera. So measurements were done at 4 times 0.06 seconds, 0.016 seconds, 0.053 seconds, and 1.1 seconds. You can see this is what I would refer to as a turbulent boundary layer. So right around here, you have very fine scales associated with it and very large scales simultaneously. And you can see that breakdown as the explosion spreads out from 0.06 to 0.016 is this sort of initiation. So the flow, or the bomb blows up, there's a large mushroom cloud, and then it starts to spread. So that's the information he had, and that was publicly available. So his argument was that if I look at this particular case and see what's happening, I can see energy release, E, and reasonably, the radius of the bomb is going to be sort of the radius of the explosion is going to be a function of time and density, air density. So if I blow up a nuclear bomb underwater, I'm going to have a different result than I have if I blow it up in air. So I have 4 variables: energy, R, rho, and time. And if I look at these, I can see there's a function that, or this depends on mass, length, and time. So again, I don't know a lot about what's happening here. I do know the units, joules, meters, kilograms per meter cubed, and time in seconds. But I have 3 variables. And from this, and this is the Buckingham pi theorem, really, I can calculate the number of dimensionless parameters. N minus R equals 1. So I have 4 variables, and I have 3 dimensions, mass, length, and time. And I can repeat E, rho, and time, and combine with R. Maybe I'll do that. E, rho, and T, and R. So what I'm doing is looking for some sort of relationship, just 2 seconds, some sort of relationship that will get me what the energy is. Go ahead.
Sorry, what do you mean by repeating the variables and then combining it?
So I want to combine energy. So in the first example we looked at coefficients of force. We combined a set of variables. In Reynolds number, we combined another set of variables. We're going to do the same thing with energy, density, and time. And we're going to use R as sort of the other variable we're interested in.
Why don't you just decide to go to 3 dimensions?
Because those are the only terms that play a role here. So if I go back to that table, way back, right here, I can say, look, I have length, L. I have density somewhere in here. Density is at the very bottom, ml minus 3. I'm taking it off of this table directly. Now again, energy should be in here somewhere. Above density? Oh, above, yeah, work energy. There you go, ml. And that's one of the reasons why you'd use a table like this, so you don't have to memorize it. So we have pi, which is what we call all of these dimensionless groups. We call them pi groups, Buckingham's pi theorem. R times e to the a, t to the b, and rho to the c. And I'm using these three variables because I have MLT that I'm going to break it down into. So I'll have three unknowns and three equations. So on the left-hand side, I expect this to be a dimensionless group, so M0, L0, T0. And then it's L times ML squared, T to the minus 2 to the power A, T to the B, and we'll fit this in, C. So for length, I will have 0 equals 1 plus 2a minus 3c. Time, I'll have 0 equals to minus 2a plus b. And for, mass, a plus c equals 0. And from this, C equals minus A equals minus 1/5, and B equals minus 2/5. There we go. So my pi group is going to be R e to the minus 1/5, t to the minus 2/5, and rho to the 1/5. Or it equals to R over e to the 1/5, rho to the 1/5, and t to the 2/5. So we expect certain things to have repeatable behavior. So if I have a nuclear explosion, I will have a very large amount of energy, but I will also know that if I take a large box of dynamite and blow it up, I can do the same measurement and get some sort of similar correlation. So only one dimensionless group out of this, f of pi 1. Pi 1 is equal to a constant, and R is equal to constant e to the 1/5, t to the 2/5, rho to the minus 1/5, and Taylor assumed that C is equal to 1, which is not a bad assumption in the end. I think he based it on previous results. I know. Okay, so he assumes C is equal to 1. He has a ratio for the radii that is now dependent on time, which he has measured in the photograph, rho, which he has basically because he knows it's being done in the atmosphere, and energy is the only one thing left. Again, this was publicly available information. So out of that, he got a relationship log R, 0.41 log of t, and plus 0.2 log of E over rho, and it ended up that the energy is 222.7 kilotons, and it was awful close to the actual result, and it resulted in a, I think he was at Cambridge at the time, a knock on the door from the FBI. So if you do really good work, somebody will